So this project was done with with collaboration with my advisor, Dr. Sham Foran at the Department of Biomedical Informatics. Here's my presentation outline. As the introduction, I described the problem of dataset shift and model drift in clinical predictive models and our proposed approach to tackle the problem. In the background section, I introduced the divergence metrics used to measure dataset shift. The method section includes descriptions of the dataset that we use in our experimental workflow. At the end, I'll present the results followed by a brief conclusion and discussion. Prediction is central to many of the key activities in medicine. In medical practice, prediction has many applications. Examples include evaluating the risk of developing disease in the future, diagnosis, prognosis, and estimating the response to therapeutics. Many clinical predictive models are regression or classification models where the model predicts a target variable from several predictor variables. Such models are trained using supervised machine learning methods where a model is derived from a training data set. The model is then used to predict target variables in an unseen test data set at application time. A fundamental assumption in supervised predictive models is that the training data from which the models are derived and the data on which the model will be applied follow the same distribution. And therefore, the model is expected to perform the same on the test and training data sets. However, in medicine, as well as in other domains, properties of data change over time and across different geographical regions and sites. This phenomenon is known as dataset shift or distribution divergence and is an important cause of failure in predictive models. In the presence of dataset shift, the performance of most statistical predictive models is likely to change for the worse. We refer to this phenomenon as model drift, where the model doesn't generalize to the test data set. For example, consider a model that is derived from a training data set from a particular hospital H1 to predict the probability of morbidity among patients with community-acquired pneumonia. If the model were to be used at a different hospital H2, its performance may decrease due to difference between data distributions. Factors such as differences in the demographics of the population, differences in clinical practice between the two hospitals are among the reasons for changes in the data distribution. A straightforward solution to model drift detection problem is to periodically reevaluate the model on new data or use approaches like domain adaptation methods to address the dataset shift problem entirely. However, typically in clinical predictive models, obtaining the target variable is expensive and time consuming. For example, in the pneumonia model I described before, the collection of the morbidity target variables, such as complicated intensive care unit stay, can be very expensive. Therefore, it is necessary to develop approaches that predict model drift while reducing or eliminating the need for the collection of target variables. Our proposed methods for detecting model drift are based on the hypothesis there's a correlation between dataset shift and model drift. Accordingly, we propose to use unsupervised distribution divergence metrics that do not require target variables to measure dataset shift and estimate model drift. So our objective in this work was to investigate the relation between unsupervised distribution divergence metrics and the performance of clinical predictive models that are derived from using supervised learning. In particular, we investigate the effect of distribution divergence across intensive care units in 12 hospitals on the performance of predictive models that are derived from one hospital and evaluated on the other hospitals. Our experiments include the prediction of mortality and long stays in the ICU, These labels are easily computable from the EHR data that we use and thus provide an abundant amount of labels for our experiments. However, in practice, we would use the proposed method for settings in which labels are not readily available and are expensive. Divergence between distributions is typically estimated empirically from samples drawn from those distributions. Popular metrics for distribution divergence are F-divergence metrics such as scale divergence, and integral probability metrics or IPMs, including maximum mean discrepancy and Wasserstein distance. It has been shown that IPM estimators have better consistency and convergence rates compared to F-divergence estimators. Therefore, in this study, we use IPMs as divergence metrics. IPMs are defined with this general form as the absolute difference of two integrals, where P and Q denote two distributions, and H is a class of real valued measurable functions. By changing the class of functions H, different metrics are obtained. In the next two slides, I describe Wasserstein distance and MMD as two metrics in the span. WD calculates the minimum cost of transporting one distribution to another. We can think of distribution as a pile of earth. WD is assumed that then assumed to be the amount of earth that needs to be moved times the mean distance that it has to be. Because of this analogy, the metric is known as the earth mover's distance. This equation here shows an empirical estimator for the WD metric for two sets of predictor variables, which is solvable linear program. Another metric in this class is MMD. This equation shows an unbiased estimator of MMD metric for two sets of predictor variables. A popular choice of function K in the equation is the Gaussian RBF kernel. Also, a non-parametric test based on this estimator is available. In our experiments, we use the p-value of the MMD test as an additional divergence matrix. We obtained data from the high-density intensive care or Hygenic dataset that contains EHR data on about 120,000 adult patients admitted to ICUs at 12 hospitals at the University of Pittsburgh Medical School Center from February 2008 through December 2014. The table here shows the number of ICU stays per hospital. The Hygenic dataset contains structured data, including demographics, vital signs, medications, and laboratory test results. Here I demonstrate the general workflow of our experiments. We started with partitioning the data by hospital into 12 data sets, H1 through H12. Each hospital HI was used as the training set, and the remaining partitions were used as test sets. For a robust analysis, we repeated each experiment multiple times and bootstrapped samples of the training data set. So here we obtained 10 bootstrap samples of the training dataset HI. The 10 bootstrap samples were used to compute pairwise divergence with the remaining 11 data partitions. The results were stored in a 10 by 11 matrix DFI. Moreover, on each bootstrap sample, a model was trained and evaluated on the remaining 11 data partitions. The model performance results were stored in a matrix DFI. And finally, for each training hospital HI, we use linear regression to determine the correlation between the model performance values EFI on the y-axis and the values of divergence, distribution divergence DFI on the x-axis. We performed two prediction tasks in the experiments, mortality prediction and length of stay prediction. Mortality prediction test is usually defined as predicting whether the patient dies during the ICU stay, given the data from the first 20 hours of the ICU stay. For length of stay prediction, we frame the task as a classification problem, that is predicting whether a patient stays longer than 3 days in the ICU, given the data from the first 24 hours. We used two classes of models, random forest and multi-layer perceptron. We trained the random forest using 3-fold cross-validation for hyperparameter tuning. For the MLP model, we used Greek search and a validation set to tune hyperparameters, including model architecture and weight decay parameters for the atom optimizer. To calculate the divergence between two data sets, we used two types of data representations, raw representation and embedding. The raw representation was the output of the data pre-processing step with 1,500 features, and were used in both experiments with both models. The embedding representation consisted of the output from the second layer, hidden layer in the MLP model, with either 100 or 500 features. This representation was only used in experiments with the MLP model. For evaluations, we used area under ROC curve to measure model performance on test data sets. To predict model performance, we used linear regression between the AUC and divergence values. We performed 10-fold cross-validations and reported the mean absolute errors. We also used the regression slopes and their p-values as correlation measures. This figure shows an example of results obtained from experiments. It shows the results from using one of the hospitals as a training data set for the mortality prediction task with the random forest model. Each panel shows a linear regression line fitted to divergence measures and AUC values. We performed similar analysis for the remaining 11 hospitals, each as a training data set, using both random forest and MLP model for both mortality and length of stay prediction tests. Here is a summary of the results for all of the experiments for mortality and length of stay prediction task. The tables show the average slope or beta and the average mean absolute error of regression models for each divergence metric. The WD or Wasserstein distance metric more strongly correlated with the AUC compared to the other metrics, although the mean absolute error values are similar across the three divergence metrics. Regression models here could predict model AUC from divergence metrics with average MAEs of 0.02 to 0.05. So in conclusion, we investigated the correlation between unsupervised distribution divergence metrics and predictive model performance. Specifically, we analyzed the effects of divergence across ICU datasets from different hospitals on predictive modeling. The results showed significant inverse correlation between WD and MMD divergence metrics and model AUC values, and direct correlation between MMD p-values and model AUC values. In most of the experiments, the correlation was statistically significant. The direction of correlation was more consistent, and the strength of the correlation was the strongest for the WD metric. There are several limitations to this study. First, we measured divergence only across marginal distribution of predictor variables. Unsupervised divergence metrics are likely to fail when changes occur in the distribution of labels. We plan to extend our investigation to other types of data sets here. The second limitation was that we investigated only one divergence scenario across hospitals. Another scenario that we plan to examine is overtime divergence at the same hospital. Third, our study was limited to data from only one hospital system. In the future, we plan to include EHR data from other hospital systems. And as a future work, we also plan to generate explanations when divergence leads to model drift, as to look at the what features actually distribution of what features change, or what combination of features change that cause a data set shift and ultimately model drift. And here are some acknowledgements. Special thanks to reviewers and financial support of NLM and ICP program at Pitt. Thank you for your attention. I will be happy to take questions.